In this lecture, we discuss about what is D'Alembert ratio test, and this D'Alembert ratio test is simply say as ratio test with examples. Let sum of n equal to 1 to infinity of un be the series of positive terms such that limit of un upon un plus 1 when n tending to infinity, which is equal to n. Then the series sum of un is convergent if L is greater than 1, divergent if L is less than 1, and test fails if L is equal to 1. Let us take one example to illustrate this D'Alembert ratio test. Test the convergence of the series sum of n square upon 3 to the power n. Let us try to solve this question. The given series is sum of un, which is equal to n square upon 3 to the power n. Now, here nth term un is equal to 1 upon n square upon 3 to the power n, and n plus 1th term, which is equal to, we have to replace n by n plus 1, then we will get the n plus 1 term. So n plus 1 whole square whole divided by 3 to the power n plus 1. Now, there is a one question here. Can we apply geometric series test over here, or P series test, or Concise nth root test, or comparison test? So definitely, we cannot use the geometric series test because this series is not into the form of geometric series. We can also not use the P series because it is also not like a P series. Okay, can we use the Concise nth root test? So yes, we can use the Concise nth root test. But here, the power of 3 is n, but the power of n is not in terms of n. So slightly it will be difficult, but we can use the Concise nth root test. Now, if all the conditions or comparison test can be used, so now yes, the power of numerator is algebraic form, but the denominator is not in the algebraic form. It is 3 to the power n. If it will be n to the power 3, then definitely we are able to use the comparison test. So clearly, we are not able to use what are the other methods we have already discussed. So we use the ratio test or D'Alembert ratio test. So simply in D'Alembert ratio test or ratio test, we have to just find the ratio of two consecutive terms. Now here we obtain un and un plus 1. Now let us consider the limit of un upon un plus 1 when n tending to infinity. Un is equal to n square upon 3 to the power n, and un plus 1 is n plus 1 whole square upon 3 to the power n. It can be simply written as n square upon 3 to the power n, and second, this will be reverse. So 3 to the power n plus 1 will goes to numerator, and n plus 1 whole square goes to denominator. Let us go ahead. Now, n square upon n plus 1, we are writing these two in the same place, numerator and denominator, and we are writing 3 to the power n plus 1 upon 3 to the power n. Again, if we simplify it, we can take n square common from the denominator over here. If we take n square, we have n square, and here 1 is remaining, 1 plus 1 upon n whole square. And here 3 to the power n plus 1 can be written as 3 into 3 to the power 1 into 3 to the power n, which gives us 3 to the power n plus 1 whole divided by 3n. So what are the common things in numerator and denominator? We have to just cancel it. What is remaining over here? 3 upon 1 plus 1 upon, if we substitute n tending to infinity, 1 upon infinity and something upon infinity is 0. So 3 upon 1 square, which is equal to 3. And clearly 3 is greater than 1. Hence, by ratio test, if L is greater than 1, then the given series is convergent. So this series is convergent by ratio test. Thank you.